Hello guys, my name is Balkrishna Srivastav and welcome to CodeWithBK. So in this video, we write a C++ program to estimate the value of natural log x using the first n terms of the series. So before we begin, it is a request to please subscribe to my channel because out of 100 viewers, only 3 to 5 are subscribed. More than 95% of my audience is not subscribed, so please subscribe to my channel. So let's begin. So we will estimate the value of natural log, which is basically ln x, using the first n terms of the series. So there is a series expansion for this, and we look at x greater than 0, okay, and for that n will be greater than 0 as well. Okay, so the series for natural log of x is basically, okay, so if you expand this, we have 2 into, so I equal to 1, okay, I start with 1, so 1 by 1 will give you 1, x minus 1 upon x plus 1, okay, 2 into 1 minus will give you 2 minus 1, so this is 1, this is for I equal to 1. For I equal to 2, we have 1 by 3, x minus 1 upon x plus 1 whole cube, plus this is y equal to 2, plus then for I equal to 3, we have 1 by 5, 2y minus 1 is 6 minus 1 5, x minus 1 upon x plus 1 to the power 5, plus 1 by 7, x minus 1 upon x plus 1 to the power 7, and so on. I equal to 3, I equal to 4. Okay, and we have to calculate this. All right, so we see two methods. In the second approach, we optimize a little bit, okay, and I'll tell you why we are trying to optimize. In the first case, we simply just absolutely calculate the series the way it is, okay. If I take x minus 1 upon x plus 1 as y, so this becomes 2 into y plus 1 by 3 y cube plus 1 by 5 y 5 plus 1 by 7 y 7, okay, for n terms, okay. So I will take values 1 to n, all right, okay, and that is what we code. So going back to my code, I'll say double is the return value. Natural log takes a double value x and the number of terms n, okay. So we have to return the sum, which will be the value of this natural log x. I'll set it to 0 and return the sum finally, okay. We are iterating from 1 till less than equal to n. So for int I equal to 1, I less than equal to n, I plus plus, okay. The ith term t is equal to, for I equal to 1 we have y, for I equal to 2 1 by 3 y cube, for y equal to I equal to 3 1 by 5 y 5. So I take y separately. Double y is x minus 1 upon x plus 1, and since x is a double, this is going to be double value as well. We don't have to worry about the integer division, okay. So term t equal to 1 by 2 I minus 1, 1 by 2 into I minus 1, okay, 1 by, sorry, divide, okay, into y to the power 2i minus 1. So pow, and I do include C math, into pow y to the power 2i minus 1, okay. All right, so this is my term I added to my sum. So 1 by 2i minus 1 for all values of I except 1 is going to give you 0, because for 1 this is going to be 2 into 1 minus 1, this is going to be 1, so 1 by 1 is 1, integer division is fine here. When we start from 2, this is going to be 2 into 2 minus 1, this is going to be 3, so 1 by 3 integer division is going to give you 0, okay. So we want this not to be 0, so we have to have either numerator or denominator or both to be of a double type. So if I change the numerator to double, so double by integer will give me a double value, and that's what we want. We don't want integer division to make it 0, okay. And finally you return, so we have calculated the sum within the bracket, so we need to do return 2 into sum, okay. So let me take some value of x 2.77, okay. In num x is how many values in this array? 4, okay. Int n, for the number of terms I keep it 20 for now. So for each value of x, okay, so I iterate the array, I get the ith value, which is the value of x. I'll say xs of I, okay. So for a value of x and the number of terms n, I want to know the value of this from this function, okay. That gives me the natural log, and I want to compare it with the inbuilt functions log, okay. So I can say, I can print this in columns, say header. So this is going to be x, the value of x, for that the value of n, the number of terms being used, then the natural log being created, being calculated, and the using the inbuilt function. Okay, so I say I use iomanip. So I'll have to use iomanip to use setw. Okay, so I've already uploaded a separate video how to use setw in a line left and right. Okay, output, formatted output, you can check out that video. Okay, so I have to say set width, say 8, and keep it on the left side for my value of x. Okay, so I print in the exact same formatted manner. Okay, so for each value of x from this array, and using the first 20 terms I get the natural log and then the corresponding log value using this x. So you don't have to pass n for x. Okay, it is automatically calculated. All right, so compile and run. Compile and run. Okay, so 0.37 for 1.45, 4.04, 4.21 close, 2.90, 2.91, 1.01. Let me make this to say 100 terms. Okay, compile and run. Okay, almost the same now. Okay, the precision is much better. So more the number of terms you add, the closer it gets to the original value. Okay, but there is a problem that we are calculating pow again and again, and pow takes time. I mean, if you are dealing with double values here and you're calculating pow, it will take time. We can find a way to remove this pow method. So how can we remove that? So we have the first term t1 as, I'll remove the 2, I'll keep the 2 outside, I'll say t1 is just the this part inside. T1 is simply x minus 1 upon x plus 1. Okay, T2 is 1 by 3 x minus 1 upon x plus 1 whole cube, which is equal to 1 by 3 x minus 1 upon x plus 1 into x minus 1 upon x plus 1 whole square. So I can take out x minus 1 upon x plus 1 as t1. So this is going to be 1 by 3 t1 into x minus 1 upon x plus 1 ka whole square. Okay, similarly I have t3 equal to 1 by 5 x minus 1 upon x plus 1 whole 5, which is equal to 1 by 5 x minus 1 upon x plus 1 whole cube into x minus 1 upon x plus 1 whole square. Okay, you multiply and divide by 3. Okay, keeping the value same. So 3 comes here, 3 by 5. So 3 by 5 into 1 by 3 x minus 1 upon x plus 1 whole cube into x minus 1 upon x plus 1 whole square, which is equal to 3 by 5. This thing is t2, 1 by 3 x minus 1 upon x plus 1 whole cube. So 3 by 5 t2 into x minus 1 upon x plus 1 whole square. Okay, similarly you have t4 as 1 by 7 x minus 1 upon x plus 1 to the power 7 equal to 1 by 7 x minus 1 upon x plus 1 to the power 5 into x minus 1 upon x plus 1 to the power whole square. Okay, you multiply, divide by 5. Okay, so this becomes, this 5 comes here. Okay, so 5 by 7 into 1 by 5 into x minus 1 upon x plus 1 whole 5 into x minus 1 upon x plus 1 whole square, this is equal to 5 by 7. Okay, this is t3. Okay, 5 by 7 t3 into x minus 1 upon x plus 2 x plus 1 whole square. Okay, so if we use x minus 1 upon x plus 1 as y, so t1 is y, t2 is this thing 1 by 3 t1 x1 x minus 1 upon x plus 1 whole square. So is equal to 1 by 3 t1 into y square. Okay, t3 is this thing 3 by 5 t2 into y square. t4 is this, okay, 5 by 7 into t3 into y square. So you can say ti is 2i minus 1 upon 2i minus 1 plus 1, okay, into ti minus 1, the previous term, into y square. Okay, I mean, I'm a master's in physics as well, and I've done this like a gazillion times. I'm actually happy doing this again after so long. Okay, So this is what comes out to be. So we can calculate recurring terms in every iteration without using power. Okay, if we can start with t1 as y, we can start with t2 like this, and then we can move on to t3, and then we can move on to t4. Okay, so if I name this 1 and if I name this 2, okay, no optimizations. Okay, optimizations not using power. Okay, so we start with sum equal to 0 and we add our first term as it is. So we say add the first term, which is basically your y, right? The t1 is y. So we say sum plus equal to y. Okay, add the first term. Okay, and I will also need a variable for previous term. So to store the previous term, double previous term is y. Okay, because we will be starting the iteration from I equal to 2, the second term. So previous term is going to be t1 in this case, so previous term is simply y. Okay, so we start with I equal to 2, go with it less than equal to n, all n terms. Okay, so double t in this case is going to be 2i minus 1 upon 2i minus 1 plus 1. So 2i minus 1 minus 1, okay, make it 2.0 so that it becomes a double. Okay, divided by 2i minus 1 plus 1. Okay, this entire thing into the previous term into y square into y. Okay, you add this to the sum and you set this previous term to t for the next iteration. Okay, because previous term for t2 is t1, so when you calculate t2 and you have to move to the third term, t2 becomes the previous term for t3. Similarly, when you calculate t3 becomes a previous term for t4. Okay, all right, and we are not using power anywhere in this case. Okay, so let me just add natural log 1 2. Okay, natural log 1 and 2. Okay, so compile and run. Okay, similar values. Okay, in fact the same values from log 1 and log 2. All right, so we are not using pow in our second function. Okay, and this should make the function a little faster than this first function, and we can check that as well. We can time the functions. Okay, I can say double output 1, it is from say natural log 1. Okay, and I will have to print this. Okay, similarly we can have output 2 from natural log 2. Okay, we got to time these functions now. So we use std chrono to measure the runtime. So we start the clock, we call the first function, and we stop the clock. Similarly, we start the clock, stop the second, call the second function and stop the clock. Okay, and we find the time elapsed between the start and stop for both the cases. Okay, so I'm printing x and natural log 1 and the time taken by it, then natural log 2, the second function called time taken by it, and the original actual value from the inbuilt function. You get output then elapsed time 1 and then output 2 and elapsed time 2. Okay, so compile and run. So time taken by the first function is always larger than the second function, you can see. Okay, and this is in nanoseconds. Okay, nanoseconds. All right, so if I increase say n to say 200, okay, the time difference increases. Okay, this takes 27,000 nanoseconds, this takes only 5,000. Okay, and that is why this second function is faster. Okay, that's why I had to use this high resolution clock. You can use system clock as well, but it will not show the difference with that much precision. Okay, so this was your C++ program to estimate the value of natural log analytics using the first n terms of the series. So if there is any doubt, there is a part you do not understand, please let me know in the comments. I always try to answer all your comments, and you can always let me know in the comments if there is a question you want to solve or if there's a concept you want to discuss. So please like this video, subscribe to my channel, and thank you for watching.